ethers may also be synthesized through an alcohol dehydration reaction. So in this reaction, we start with 2 alcohols, at least 2, and we'll keep it general, ROH. So the R group is an alkyl chain, carbon-hydrogen chain. And we have an alcohol. And when we do alcohol dehydration, remember in the Williamson synthesis, we use a strong base. In this reaction, a strong acid is used. So a classic strong acid, sulfuric acid, H2SO4. Other strong acids are okay to use as well. And then typically some heat is used in this reaction as well to help the reaction move along. And we're just looking at the reaction scheme here, then we'll go through an example with the mechanism. But if we have 2 ROH, so 2 alcohols, what ends up being produced in this reaction is an ether where the R groups come from the 2 alcohols. So the same R group from 2 different alcohol molecules will become the 2 R groups in the ether. So we have alcohol, acid, and the ether. Now, if we have 2 alcohols present in a alcohol dehydration reaction to synthesize ethers, then it's possible that the 2 R groups on the ether will be different, and we'll look at that in an example. So this is the general synthesis, pretty simple here. Let's go through the mechanism with an example. And we'll use 2 ethanols. I think here will be useful to note that sometimes you'll see the equivalence of reagents stated, where it'll say 2 equivalents of reagents, or 3 equivalents, or 1 equivalent. Other times it's not stated at all. Usually you can assume that you have excess reagents, and if that's ever relevant on in-class work or challenge homeworks or assessments, it'll be explicitly said to you. So it might not state that you have 2 alcohols present. It could be the alcohols are in excess and the reaction will still be carried through. So if we have 2 alcohols, we have a strong acid, we have some heat. This reaction is about 140 degrees Celsius. Then if we just predict the product here, we take the same R group from the alcohol, keep 1 oxygen from 1 of the alcohol molecules, and we have diethyl ether here. So here's the R group, here's the same R group. In the mechanism here, we start with an alcohol, and we have the strong acid H2SO4. This is the structure of H2SO4. This is in a pKa table that will be provided for you. This is a strong acid. So since we're working with a strong acid, pKa of about -9, it's a much stronger acid than the alcohol. So in this case, when the strong acid is present, the alcohol acts as the base. And so the oxygen part of the alcohol, so this is the only atom in the alcohol molecule that has non-bonding electrons. That's the only atom that can create a new bond with its non-bonding electrons. It will take a proton from the strong acid, sulfuric acid, and then sulfuric acid, that oxygen will take electrons from the oxygen to hydrogen bond. So the ethyl part stays the same. We still have the OH from the alcohol. Oxygen still has one set of non-bonding electrons. And then I'll use this orange color to demonstrate this is the new bond to the hydrogen from sulfuric acid. Oxygen lost ownership of electrons. It's now sharing 2 instead of owning 2, so it has a positive charge. And then we have the conjugate base of sulfuric acid. Negative charge on that oxygen that lost the proton but gained the electrons in the bond. So on this alcohol molecule, we now have, use this lighter blue here, we now have an H2O group. This is a good leaving group. We've used this, we've protonated alcohols in Organic Chemistry 1 to make good leaving groups. We will do this in future reactions this semester as well. But once you have the H2O, or the oxygen is still bonded to part of another molecule, that H2O is a good leaving group. So I'm going to redraw that protonated alcohol for this next step. We have a good leaving group. We also have another alcohol molecule. Where the oxygen in that neutral alcohol molecule has electrons, it can create a new bond. We're doing another substitution reaction here, where the oxygen from the neutral alcohol can create a bond to the carbon that's bonded to the good leaving group, and the leaving group will leave. Then we have still CH3, CH2 from the original protonated alcohol. That CH2 to oxygen bond broke, but now we have a new bond. So here's our new bond to the neutral alcohol. This oxygen is still bonded to a hydrogen, and then it's bonded to the CH2, CH3 group. Our byproduct in this step is water, H2O. So we have a protonated ether. We're almost at the ether molecule, but we have a protonated ether here. If there is excess ethanol, here we said we need at least 2 ethanols to carry out this reaction. If we have excess ethanol, then we have protonated and deprotonated ether in equilibrium with protonated and deprotonated alcohol. So let's write this out. So the So if we have our protonated ether, I'm just going to copy down the structure, CH3, CH2, OH, positive charge on oxygen with one lone pair, and then CH2, CH3. Now this reaction, since we're carrying the reaction out in an alcohol or with an alcohol, you can imagine a beaker of ethanol adding some sulfuric acid to it, and this reaction can take place. So since we have excess alcohol, there are some ethanol molecules that had not gotten protonated by the sulfuric acid, so they're still present as a neutral alcohol in solution. They can exist in equilibrium with the deprotonated ether. And protonated alcohol. So now, if you remember, this is called a alcohol dehydration reaction. It's called alcohol dehydration because we lose an H2O molecule. That was our good leaving group. It breaks off as a byproduct, so this is why it's called a dehydration reaction. And then at the very end, we have protonated ether and ethanol in equilibrium. Now you might note that the conjugate acid of sulfuric acid, or the conjugate base of sulfuric acid, is not present in this equilibrium. That's because sulfuric acid has such a low pKa that it will remain deprotonated. Protonated ether and protonated ethanol or alcohols have more similar pKa's, so they will exist in the equilibrium with each other rather than sulfuric acid being present.